Welcome to Real Physics. Today I will talk about the Aether electron, a remarkable topological defect. A more technical account of this you will find in my paper, which was published last year in the Journal of Applied Mathematics and Mechanics, and the entire issue is dedicated to ether theories of elastic continua. That means that it's not such a bad idea. And the most interesting ether theory of the 19th century, you might want to watch this video about it, is in my view Cullagh's theory of the incompressible ether, and he had the idea that the rotation of volume elements corresponds to the electric field and the velocity of these volume elements to the magnetic field. And the very interesting consequence is that it works perfectly. You obtain Maxwell's equations by pure vector analysis. The only problem is you have no charges. And it's not a small problem because it's by definition, if you apply the vector analysis rules such as curl of divergence, you get zero. That means no charges. And the solution is that you consider nonlinear continuum mechanics. That means huge deformation, and I want to show you a solution to this problem. And well, I would like to tell you about the way I arrived at that solution. You might also watch this video about ether and relativity and why there is no contradictions. I started from considering defects in crystals, which are called dislocations, and there is a deep connection to the mathematics Einstein and the French mathematician Cartan considered in the 1930s as unified field theory as an extension of general relativity. By doing so, they considered the notion of torsion, which is an infinitesimal version of dislocation density. And while playing with these formula, I discovered that a very interesting quantity would be the antisymmetric part of torsion, and this would in turn correspond to screw dislocations. Now, of course, if you want to think about particles, I mean, dislocations are extended singularities, so if you want to think about particles, you would consider closed dislocation loops, and the question is, what should you imagine as a closed dislocation loops? If you have a edge dislocation, you can imagine a closed dislocation loop simply by putting an extra layer of atoms in the midst of a material. That would create an edge dislocation here and here and here and here. And yeah, or equivalently, you remove that material and let the rest respond elastically. You have a closed edge dislocation. The problem is it's not that easy to construct a closed screw dislocation loops. What you can do is, what you shouldn't do with a book, to cut that surface, so to speak, and then shift it like this. You would create again an edge dislocation, because it's like inserting an extra layer of material here and an edge dislocation of opposite sign at the other side. And here you have indeed a screw dislocation, because if you walk around this singularity line, you're lifted upwards one floor, as in the case of a circular staircase. And again here a screw dislocation. However, all this is a mixed dislocation loop and not a screw dislocation loop, because you cut the material and shifted it. Okay, so what you can imagine is instead of cutting a material and shifting it, imagine a circular surface. Everything is embedded in this material. I cut this material here, thought experiment, and then I twist the respective ends with a certain angle. Indeed, you would create something like a screw dislocation, and the entire thing would be a closed screw dislocation loop. The problem is, however, you are destroying the crystal structure. That means not only at the singularity line, but also at the entire surface. The crystal orientations wouldn't fit together any longer. And this is a problem. You can't do that in that kind of geometry if you consider curvature and torsion. So, or better, only curvature, only torsion, sorry. But what you can do, and now we arrive at nonlinear continuum mechanics, you can cut this surface and twist it not by a little angle but by 2 pi and then put it together. That would of course cause huge deformations in the vicinity of this singularity line, but as a matter of principle it is possible. So I searched a lot the literature and I discovered this very interesting publication. Look at this, 1906, the eminent Irish physicist Joseph Larmor. There are so many smart Irish physicists, Larmor and Cullagh and Hamilton. And he said, if breach, I have visualized this here, this would be the cut surface, and you could take out this torus in order to do the twist. And he said, if breach of continuity is produced across an element of interface in the midst of an incompressible medium, for example, by creation of a lens-shade cavity, and the material on the one side of the breach is twisted round in its shape, and continuity is then restored by cementing the two sides together. So the idea was more than 100 years old, but however, it we can visualize it again. If you think about this defect inside an elastic continuum, it would be a source of intrinsic rotational strain. You can visualize this also as like twisting of a material. Mind that I can do this in 2 ways. Apply a right-hand screw sense as a torque. That means twisting clockwise here and twisting clockwise here, or twisting anti-clockwise. That produces a screw sense of the other sign. And if you imagine that such a defect is located inside a sphere, more or less the deformation of the material would look like that outside. Now, however, if you think about again the cut surface, Cullagh stated that the rotation of volume elements is something like an electric field, and now we have the interesting fact that if you talk about finite rotations, and if you talk about huge angles like pi, you can't distinguish the direction of the electric field, because pi as a twist is equivalent of course to minus pi, but that would mean the opposite direction of an electric field coming out respectively on top and on the bottom would be the same deformation, but would count as a source of the electric field in Cullagh's theory. So you have such a defect, and that of course, if you think about integrating this about a surface, you have the Gaussian surface integral, and this would look like a charge which is included there. Of course, again, you have the both possibilities, clockwise, anti-clockwise, or better right and left-handed screw sense. And then, well, it just solves the problem. Now you have that source of intrinsic rotation, but you must not apply vector analysis any longer, and you need to describe that with the anti-symmetric part of the torsion tensor. This is all still very difficult, and what I did is additionally I tried to calculate the elastic energy in a paper applying a toroidal coordinate system by considering then huge deformations, and I got some very nice solutions. And well, still I did not succeed in calculating something reasonable which would correspond to something like a self-energy of an electron. And for the rest, I don't think that anybody else read the paper. No, just a few people, but that's science. And yeah, just one remark, this would also be the same kind of distortion if you're familiar with it. That's a Volterra distortion of the 5th kind. So I want to show you some different names to summarize. The idea is to build a closed screw dislocation, which is not possible in a technical sense, and you can call also that a circular twist disclination. Disclination is something else if you consider defects in crystals, or Volterra distortion of the 5th kinds. I also want to give credit to this Polish physicist Dominik Rogula. He also described this defect in 1976, and of course Joseph Larmor did that more than 100 years ago. But there is still one very interesting topological defect I mentioned that larmor defect as a cut and glue process. You rejoin the surfaces after twisting by 2 pi. So to speak, if you walk through this defect, you would have done an entire rotation of 2 pi. But there is another defect discussed in the literature, Shankar monopole, and this is indeed a twist of 4 pi if you walk through the defect. Let me explain that better. You can imagine a tripod in every point of the continuum. That means something like S3 or SO3, the rotation, possible rotations in 3-dimensional space. Just imagine that arbitrarily oriented tripod, and at infinity, let's say it's in an undisturbed position, and then you, by walking towards the center, you do one twist of 2 pi. So in the center you again at identity, as in the case of infinity, and you can do that from every direction. That means you have at this point spherical symmetry, and you don't have any singularity anymore. That's very interesting, because you have kind of an isotropic defect that somehow represents a double electron or 2 electrons superimposed on top of each other. Still, you cannot do that with a usually ordinary material. You need to postulate other things, and we are entering also a mathematical description here. I will not go into details, but you need to talk about homology and homotopy groups. This Shankar monopole corresponding, so to speak, to 2 electrons would have a vanishing first homotopy group. The larmor defect not, it's not simply connected, but the Shankar monopole would be a non-trivial element of the 3rd homotopy group of such an elastic continuum, or such a fiber bundle, and the 3rd homotopy group is just the integers, for who is interested in topology. Now in my next video I will consider the distortions caused by this larmor defect. I said this would be more or less the deformation if you have one larmor defect inside an elastic continuum, and you can now think about what happens if you have more or a variety of such defects, and visualize that these dark areas correspond to a rotational distortion. You have rotation, rotation, rotation here, and in the mid of 2 rotations, it's like that. If you rotate these, in the middle here, you have a shear distortion that would correspond to the white edges here of this dodecahedral symmetry. And more or less, what about the region between 2 charges, in this case opposite charges? If both are twisted in the same direction, you have a twist of the entire cylinder here. How to imagine this, I will discuss in my next video. However, as I said, you find a more technical summary in this paper, and there is also a precursor, what can physics learn from continuum mechanics. And as a more general remark, modern physics usually does not deal any longer with these fundamental questions. What does the electron consist of? Can we calculate the self-energy of an electron? All these fundamental questions were important 100 years ago, but there was a big change in scientific culture, in the way people thought about problems. The European tradition was oriented in a natural philosophical way. They were asking how matter is constituted in its inmost folds, and after the war, the American tradition of physicists, they were just interested in applications and huge projects and describing the experiments rather than arrive at a fundamental understanding. And I described this in my last book, Make Physics Great Again. You find reference to the ether theories, but also to other problems, and I think that's the basic reason for the mess modern physics finds itself in. If you enjoyed the video, don't forget to like it, and you are interested in fundamental questions, subscribe to this channel.